we're going to now take our integrals up a notch, and instead of having just a rectangular region, we're going to have arbitrary regions that we have to integrate over. So finding the bounds is going to be a lot more difficult, and if I want to switch order of integration, that is also going to be more complicated than just being able to swap the two. So what I want to do is kind of set this up. In some instances, you're going to be given the integral, and you might need to change the bounds, or you're going to have to pick which is the appropriate order of integration. Do you do x then y, or y then x? And it can depend on a couple different things. But here, we're going to let f of x, y, be a continuous function on a region R. Which is bounded by the curves x equals a, x equals b, y is potentially some function of x, and y is potentially another function of x. Okay? So essentially what's going on here is here's what's happening in the xy plane. X is varying between the constants a and b. But then in y's direction, I have maybe some functions. So let's say ends up looking like this. This is the line x equals a. This is the line x equals b. But up here, I have some bound, which is y is some function of x. And down here, maybe I have a straight line. Y is a different function of x. Okay. This is our region of integration R. So if I want the volume of my function over this particular region, then the double integral over R of our function with respect to x and y, in this case, is going to be much easier to do in one particular way. So because x is changing between constants, remember we're finding a volume, so I should integrate with respect to x last because this has constant bounds. However, my y has function bounds that depend on that outer variable x. So my y value is starting at this bottom function and going up to the top. So the lower bound here would be g1 of x, and the upper bound here would be whatever that function g2 is. Because what happens is then when you find this integral, you'll evaluate y at these functions of x, and again it turns it solely into an integral dealing with x. All of your y's will disappear. So here you do y first, then x. Now instead, if I have the opposite, if I'm given maybe my y as constant bounds, but my x is variable, then I want to do the opposite thing. So on the counter part, suppose f is a continuous function on the region R, which is bounded by the curves y equals a constant c, y equals a constant d, and then x is these functions of y potentially. So same idea here, because x is bounded by something dealing with y, it's going to make more sense to integrate with respect to x first and then y, because y has the constant bounds c and d. So here, maybe this looks like this. Here's y equals d. And then maybe y equals c ends up being down here. And then we've got x being some function. Maybe it's got some kind of curve to it. Looks something like this. The rightmost will be the second function, h2 of y, and the innermost closest to the y-axis will be h1 of y. So this is my region I'm integrating over. So if I want to find the volume of the solid over this region for that function, again, it's going to be a double integral. And I'm going to have two variables of integration. Because y is constant bounds, that's going to be the second integral I do. I'll integrate with respect to x first. So my y will change between c and d, and then my x starts at the leftmost curve and goes to the right. So this will be h1 of y to h2 of y. Okay. So switching your bounds is not as clear-cut when there's functions, because it's not as easy as just flopping the order. You have to actually figure out the curves this thing is changing between. So to start, we're going to go ahead and evaluate an integral. It's one that we can just do straight through. However, I'm going to also show you how to switch the bounds for that. So being able to draw a good image for the region of integration will help you a ton. So the first example we're going to start with is we're going to evaluate the integral from 0 to 1, the integral from 2x to 2 of the function x minus y, and then this order is dy dx. So what I want to start with is I want to find the region of integration. Again, that's going to help me for swapping bounds. I'm going to do this off to the right, so then off to the left I can actually calculate the integral. So go ahead and draw my xy axes. And so starting with the outermost piece, this deals with x. So what you can do to actually get the equations and say x equals 1, x equals 0. So in my x direction, I only have to go out really a distance of 1. And I'm going to go ahead and draw these two lines, which really just ends up one of them overlapping the y-axis. This is x equals 0. And then this is the other line, x equals 1. I'll move that over. Okay. Then I'm going to move on to other bounds, which deal with y. So this is the equation y equals 2, and this is the equation y equals 2x. Well, y equals 2 is just a horizontal line, so that's the line right up here. And then if I graph y equals 2x, that's a line with slope 2. It goes through the origin. Slope 2 would mean up 2 over 1. Or really, when you plug in 1, the output for y is 2. So this is the line y equals 2x. So when I'm finding the region of integration, I'm looking for something that is completely bounded. It might be natural to want to say here, but you see we don't have any of our curves on this. Instead, my triangle is this region up here because it's bounded by these 3 curves. This just helps me with those constant bounds. So my region of integration is the upper part of this triangle. Okay. So again, this is just going to help us when we switch those bounds, but for right now, what we can do is just go ahead and directly evaluate this integral. So we want from 0 to 1, we want from 2x to 2 of x minus y dy dx. And again, I'm just going to call this I, so I don't have to keep rewriting this whole thing every single time. So I want to integrate this inside expression with respect to y. So beginning, the antiderivative of x with respect to y is xy. Antiderivative of negative y is negative 1/2 y squared. And then we're going to evaluate this from 2x to 2 and then integrate with respect to x. So again, we're going to replace y by this constant and this function. And in the end, it'll just give me an expression that deals with x, which is nice. So going through, plugging in the upper bound, when I plug in 2, that gives me 2 times x minus 1/2 times 2 squared. I'll clean that up in a little bit. And then I've got to subtract plugging in 2x, so that's x times 2x minus 1/2 times 2x squared. And then once I clean this up, I'm left with just an integral dealing with x that I can go through and solve. So I definitely need to do some algebra to make this simpler to integrate. This is 2x. 2 squared divided by 2 just gives you a 2. And then here, this is minus 2x squared. Then 2x squared is 4x squared times 1/2 really gives you a minus 2x squared, which is super nice because these just cancel. So that is gone. So really we're just finding the integral from 0 to 1 of 2x minus 2. And then that is just a nice polynomial we reverse. So its antiderivative is x squared minus 2x, evaluated from 0 to 1. Plugging in 1 gives us 1 minus 2. Plugging in 0 is 0 minus 0. So 1 minus 2 gives us negative 1. So this integral is equal to negative 1. So what I want to do now is I want to do the same thing, but I'm going to switch the order of integration. So instead now, let's integrate with respect to x first. So I'm going to go ahead and grab this up here. And I'm going to go ahead and make a copy of it. Okay. So what happened before is because we were doing dy dx, our x could change anywhere between 0 and 1. But our y value would always start at this line and go up to 2. So it always started here, go up to 2. So once you picked an x, your y value started at the line and went up to 2. So that's exactly these bounds. Regardless of the x you picked, because that freedom came afterwards, you started at the line 2x and went up to 2. And then your choices for x were anything between 0 and 1, so those constant bounds. Now what I want to do is the opposite. So I want to integrate with respect to x first. So my y bounds are going to be constants, which mean y has the freedom to be any number between 0 and 2. So depending on the y value you pick, maybe I pick this one, I'm going to start at this line and I'm going to continue out to the line y equals 2x. If I pick this y value, you still start at x equals 0 and go out to this line. If I pick this y value, you still start at 0 and go out to this line. The problem is I need to switch this as well. I need to get this as x in terms of y because I don't want to keep x in my bound. I'm getting rid of the x first. I want to integrate with respect to x. I should have no x's left. So instead, I just want to rearrange this equation. My x is equal to 1/2 y. Okay. So here, what's going on is x always starts at the line x equals 0 and goes out to the curve x equals 1/2 y. And then y changes between the constants 0 and 2. So our integral, which originally was from 0 to 1 of 2x to 2, x minus y dy dx. If I want to switch this order and ignore the bounds, and I want to do x first, then y. This outermost is again the constants. So y changes between the constants 0 and 2 because I don't want any variables in the end. But now when I go for x, I start at this function and go to this line. And again, I don't want, if I'm integrating with respect to x, to have x in my bounds. So both of these need to be in terms of y. So going with that, x starts at 0 and goes to the line 1/2 y. I can have y in my bounds because I'm going to integrate with respect to y afterwards. Okay. So you can see right here, I cannot, under any circumstances, swap the bounds when I have variables in my limits. Okay. If I tried to do that, if I integrated and just swap these, you're going to evaluate at this part last. So you're going to plug in 2x at the very end of your problem. You no longer have a volume, you have an expression that this integral is equal to, and that's not correct. These are finding the volumes of the solids underneath this particular function. So do not fall into that habit of just swapping. So here, the order of integration matters. We just can't swap bounds. It is only constant bounds. Okay. But now that I have this set up, we can go ahead and we can integrate in this order. So starting out, why did my 2 disappear? There we go. Starting out, we're going to integrate the inside with respect to x. So this would be 1/2 x squared. Antiderivative of y would just get an x attached to it. And then we evaluate from 0 to 1/2 y. And again, we are plugging this in for x, because my x should disappear and leave me with just an integral of y. So going through and plugging this in, that would give us 1/2 times 1/2 y squared minus y times 1/2 y. And at least when we plug in 0 for x, both of these disappear. So this one is thankfully gone. So I want to clean this up a little bit first. You've got 1/2 squared, that's 1/4, times 1/2, that gives you 1/8, and then y squared. Here, that gives us minus 1/2 y squared. And then at this point, you technically could integrate, but it's y squared minus y squared. So just go ahead and subtract the coefficients. And if you do 1/8 minus 1/2, this will be negative 3/8 y squared. Now I can go ahead and I can take the antiderivative. So that would give us negative. You'd get y cubed over 3. But in doing so, what ends up happening is the 3's cancel. So this is negative 1/8 y cubed, evaluated from 0 to 2. So plugging that in gives us negative 1/8. 2 cubed is going to be 8, and then 0 cubed is 0. So this ends up equaling negative 1, which is exactly what we got for the other order of integration. Okay. So in this one, it's not too terrible to do either order. And again, it's really going to be a personal preference up to you for some problems, because you can do either order or either integration. But there's two things you want to kind of keep in mind. First thing is go ahead and draw your bounds, because that might tell you immediately which one is a little bit nicer. The other thing you need to do is look at the function you're integrating over. That might tell you one integration is much easier, so I want to do that first, and then hopefully my integral becomes a little bit nicer as a result for the other variable. So we're going to do a bunch of examples of this so you can see. So let's try another example then. Here we want to evaluate the double integral over the region R of y over x to the 5th plus 1 dA. Specifically, where R is given by the xy values such that x is changing between 0 and 1, and y is changing between 0 and x squared. Okay. So I can go ahead and I can draw my region first. However, just looking at this integral, I can immediately tell you it's going to be easier to set this up integrating with respect to y first. Because if I look at this inside expression, the antiderivative of y is much nicer. It's 1/2 y squared over this thing. But if I were to integrate with respect to x, you'd have to be able to tell me what the antiderivative of 1 over x to the 5th plus 1 is. And I really don't know that, because I can't quite make a use of, it's not quite a chain rule problem. Because if I let my u be x to the 5th plus 1, I'm missing the x to the 4th component to get sucked into the du. So this integration is way too complicated for me to want to deal with. So immediately that tells me integrating y first is going to be the better option between the two. So let's try to summarize this. If we set up the integral as dA equaling integrating with respect to x first, we'll run into a lot of issues. Since the integral of y over x to the fifth plus 1 dx is complicated. So without even knowing what my region looks like, I still want to try to set this up with respect to y first. So that tells me x should have constant bounds, y can have function bounds that deal with x. So I'm going to go ahead and start by drawing this region off to the side. So we've got the two lines, x is changing between 0 and 1. So our x bounds are exactly those lines. X equals 0 is right here, and x equals 1 is right here. Then when I go through and do these bounds, the first one is y equals 0, which is the x-axis. And then my other bound is y equals x squared, which is a parabola. It goes through 0, 0, and if I plug in x equals 1, my y value will also be 1. So it goes right up here through 1, 1, and then it's got this shape. So the only thing that is enclosed by all of my curves is this region right here. So this is exactly R. Okay. So let's kind of do our integral simultaneously. Again, I always like calling these things R or I. So I want two integrals, give myself some space. I want to integrate with respect to y first because that's easier, and then integrate with respect to x. My outer bound is always the easiest because that has to be the constants x is changing between. So my outermost bound is from 0 to 1. Now, for the inner bound, for my y values, if I pick an x value, say right here, my y value is always starting at the bottom and going up to x squared. If I pick right here, you're still starting at 0 in this region and going up to x squared. Pick this point, starting at 0, going to x squared. So our bounds are 0 to x squared. If I did want to change this order of integration, your y bounds would be from 0 to 1, and then your x would have to start here and go to 1. Start here, go to 1. So in that case, your bounds would be from x equals the square root of y. So you'd start at square root of y and go to 1. Square root of y, go to 1. Okay. But again, we don't want to do that order of integration because it would be messy. So hopefully in the process now of integrating with respect to y first, it's going to make my x integral much easier. So we can go ahead and we can take our antiderivative now. The x to the fifth plus 1 is treated like a constant. Antiderivative of y is 1/2 y squared. And I want to evaluate y at these bounds. So starting with my upper bound, this would be 1/2 x squared squared over x to the fifth plus 1. And then thankfully, at least when you plug in 0, this second one disappears completely. So this one is gone. So going through, I can take this 1/2 now out front. And this is the integral from 0 to 1. X squared squared is going to be x to the fourth divided by x to the fifth plus 1. And now this is something I can actually do. We're just going to make a u sub. So it turns into a calculus 1 problem. We let u equal our denominator. Then du will be 5x to the fourth dx. I don't have that 5, but that's okay. 1/5 du is x to the fourth dx. I also want to change over my limits as well, so I don't have to go back. When x is equal to 0 for my lower bound, my u is 0 to the fifth plus 1, so we get 1. When x equals 1, u is 1 to the fifth plus 1, so u is 2. So this way I don't need to go back to my starting variable. This becomes 1/2. I get that 1/5 from the du. My new bounds are 1 to 2, and we've got 1 over u du. Antiderivative of 1 over u is natural log of u. So this gives us 1/10 natural log, and then don't forget your absolute values. And then this gets evaluated from 1 to 2. So plugging in 2 gives me natural, the absolute value of 2. Plugging in 1 gives me natural log of 1. But remember, natural log of 1 is 0. So really, this ends up equaling 1/10 natural log of 2. Okay. All right, let's try another one. Again, drawing pictures is pretty much necessary for these. And when we're about to get to triple integrals, same thing. So let's evaluate this, where R is the region bounded by y equals x, y equals 4, and x equals 0. And so this one, technically you can do either way. However, because there's only one thing dealing with x, it's probably easiest to integrate with respect to x first. You can integrate with respect to y. However, you would have to do by parts because you have y squared times an exponential function. And you might even have to do by parts twice as a result of that. So it's doable, but it's definitely easier if I'm looking for those two variables to take the antiderivative of e to the xy. So that's going to be the way I want to set up this problem. So we can set this up as dy dx or dx dy. But integrating with respect to x first will be easier. If we integrate with respect to y, we would need to use integration by parts. And I would prefer to avoid that. All right, so we're sitting a lot better. We need to draw this region though to figure out the order of my bounds. And we've got the line y equals x, which we know is just going to cut this right in half. We've got y equals 4 and x equals 0. So I'm just going to go out 4 in every direction. So y equals x goes through 0, 0, and cuts this in half. I'm going to have to move that. And it goes through the point 4, 4. Then we've got y equals 4, which is a horizontal line. And then we have x equals 0, which is just the y-axis. So the only thing that gets bounded by these three things is this triangular region. So here is R. So our integral, just copying it down, and then we'll figure out these bounds. Again, we want to integrate with respect to x first. So the outer bound is the easiest. That's the constants y is changing between. So my smallest y value is 0, my biggest y value is 4. So the outermost bounds are from 0 to 4. Okay. So when I go to find the inner bounds of x, my y is free. So I can pick whatever y value I want. And regardless of the y value I pick, it's always starting at 0 and it's going over to this line. 0 to this line. 0 to this line. So my lower bound is 0. And I want my upper bound. And again, the only variables I can use are the outermost ones. So I don't want x in the top bounds. That means my upper bound is y, because this equation is just interchangeable. My upper bound here is y. Okay. And now I just go ahead and integrate. Just to kind of make life easier, again, y squared is a constant with respect to x, so it pops out. You're really just looking for the integral of e to the xy. And to avoid, again, u-subs are a little bit hard here because you have the variables. So I'm going to do this without bounds off to the side. I don't want to say these two things are equal because I want to just be able to find this component and then come back up here to my thing with bounds. So if I do this, the y squared can pop out and you're left with e to the xy dx. You don't need to make a u-sub because you can think in your head, well, if this was e to the 2x, its antiderivative would be e to the 2x divided by 2. So really the same thing happens. The antiderivative is e to the xy divided by y. But if you want a u-sub to see that, your u would be the full expression. So du would be y dx. Okay. And you can break this down, but also you can just treat y like a constant, divide it to the other side, and you get 1 over y du is exactly dx. So this becomes y squared e to the u 1 over y du. And then grouping those like pieces, y squared over y just gives us y. And then you're integrating e to the u du. Antiderivative of e to the u is e to the u. And then going back to the starting variable, this is y e to the xy. Okay. But again, you don't need to do this off to the side. This is just treating y like a constant. So the antiderivative of e to the xy is e to the xy divided by y. And so when you have that y squared out front, it ends up being y squared over y. But if you need to do it off to the side, absolutely. So here, the inside's antiderivative is y e to the xy, evaluated from 0 to y. And then we integrate with respect to y. So again, I'm replacing x by these expressions. So this becomes the integral from 0 to 4. When I plug in the upper bound, that's y to the e to the y times y. So that's y squared minus y e to the 0. And unfortunately, that doesn't disappear. E to the 0 is 1. So you could actually break this into two integrals, the integral from 0 to 4 of e to the y squared, and then the integral from 0 to 4 of y. Okay. If you feel comfortable, again, doing this without a u sub, absolutely go ahead. Because y squared's derivative is 2y. The only thing you're missing out front is a 2. So you really have a 1/2 y. But here, now because it's just Calc 1 integrals, I can go ahead and do a u sub directly in this problem. So we let u equal y squared. Du is then 2y dy. I don't have the 2, but that's not a problem. You just bring it as a 1/2. And then I also want to change the limits. So when y is equal to 0, u is 0 squared. When y is equal to 4, u is equal to 4 squared. So this front one will become 1/2 the integral from 0 to 16 of e to the u du. The second one, however, we can just go ahead and integrate. That's minus 1/2 y squared, and this gets evaluated from 0 to 4. So you may want to put a parenthesis in the front here because that minus distributes afterwards. And now, absolutely no issues finding the antiderivative. It's e to the u, evaluated from 0 to 16. Then here, plugging in the upper bound, that's 1/2 times 4 squared minus 1/2 times 0 squared. On the front part now, this is 1/2 e to the 16th minus 1/2 e to the 0. And then at least here, this is gone. 4 squared is 16, so times 1/2 gives us a minus 8. You left it like this, not a problem, but again, e to the 0 is 1, so you really have minus 1/2 minus 8. So if you want this fully simplified, that would combine to negative 17 over 2. Okay. So be very careful writing these. Also make sure you are showing all of your work. You can't just take a bunch of steps. You've got to draw the region of integration to be able to set up the bounds appropriately. The last thing we're going to do is kind of a special example. So if we have a rectangular region, again, only going to work for rectangular, and maybe I have a function that we call separable. So basically, let's see if we have one. I'm going to be able to write this as a function of x times a function of y. So unfortunately here, this one is not separable. And then back up here, however, this you can separate because this is y times 1 over x to the 5th plus 1. So I'm able to break that down as a function of y times a function of x. If I can do that and I have a rectangular region, instead of doing this iteration, what I can do is really just break apart the integral separately. And I will show you a proof of this because it's only 3 lines. So this last one is a theorem, and then we'll have one example of that. So suppose that you can write your function as a function of x times a function of y, where these functions g and h are continuous on a rectangular region. R. So our x is changing between a and b, y is changing between c and d. And again, emphasis, it only is good for rectangular regions. Then, if I want to find the double integral of f over this region, what I can do instead is integrate the component dealing with x and the component dealing with y, and then just multiply the two. Okay. So you're able to separate the integral completely. But again, it only works if it's constant bounds, because back up here, even though I could separate the two, the problem is you can't separate the bounds because y depends on x, so it's not truly separable. So this only works with constants. So again, if I can give you the proof, I'm going to try to, if it's not too long. And this one is nice. So in this case, because we have this ability to rewrite our function, this is an integral, and the inside function is g of x times h of y. We can do whatever order of integration because it's a rectangular, so let's do dx dy, which means this inside has the bounds a to b, the outside has the bounds c to d. So what happens is here, when I'm going through this first integral, this is treated like a constant, so I'm really able to pop it out front of the integral. So what we can do is we can pop this out front, and then instead do this piece first. Okay. Because h of y is treated like a constant with respect to x. Well, then in the same manner, this is just going to be a number. It's representing the area under the curve G from A to B. So you can take this whole thing and pop it out front of this integral. So this becomes this first integral times the second. Okay. So I just have one more example of this so you can see if you're able to do this, it's the best. It saves you a ton of time because then it's just two Calc 1 integrals. But it doesn't always happen. However, we are about to go through different coordinate systems, and we're going to see that when I switch to a different coordinate system, it's nice because it will likely end up giving constant bounds, which is the best kind. So I got one more example. And let's actually even just move this onto a new page so I don't have that line in the way. Let's evaluate the integral from 0 to 1, from 0 to 3 of e to the x plus 3y dx dy. So again, very nice because I have constant bounds. I don't need to do this. I could find the antiderivative of this function. However, I want to see, can I separate it? And really, because I have the addition of this exponents, I can. So the inside, we can break down, and I'll save that for one next step. Because we know if we have the same base, we add exponents, we can break it down in the same way. So e to the x plus y is the same as e to the x times e to the 3y, and then integrated with respect to x and respect to y. So my x is, or my function dealing with x is e to the x, and because that's the variable that's first, my bounds on that are 0 to 3. And then we've got e to the 3y, which deals with y, and those bounds are 0 to 1. So instead of taking this step by step, I can separate this as the integral from 0 to 3 of e to the x dx, and then the integral from 0 to 1 of e to the 3y dy. You can take it one integral at a time now, and then just combine them at the end. Antiderivative of e to the x is e to the x, evaluated from 0 to 3, which is really e to the third minus e to the 0. And e to the 0 is just 1. So this front one becomes e to the third minus 1. Now I'll go back and do this integral because I like doing one at a time as opposed to doing one step on each. Integral of e to the 3y is e to the 3y, but I've got to factor in that constant, so I need to divide by 1/3 and then integrate from 0 to 1. So this is 1/3 e to the third minus 1/3 e to the 0. And then realistically, they both have a 1/3 in common, so I can just go ahead and pop that out front, because what you're left with then is e cubed minus 1. And then just for good measure, to make this look nicer, because this is the same thing multiplied by itself, you really get e cubed minus 1 squared. So again, if you can do this, it is definitely worth doing, but it only works when we have constant bounds. So what we still have to come is we've got to talk about when I have double integrals and I have harder bounds, maybe in forms of circles or trig functions. What can we do in that case? And then we'll also talk about triple integrals and then also ways to convert triple integrals.